Okay, so we're going to look over all of quantum physics for Unit 2. Right, but I'm actually going to start off by looking at the electromagnetic spectrum. I didn't do that in the waves lecture, so I'll go over this, and it links in with quantum physics obviously anyway, so that should be fine, it makes sense to have it here. The electromagnetic spectrum, that includes waves that are of the same type, but they have a range of wavelengths and a range of frequencies. And we group them in 7 regions because they have similar properties. Now, what I'll do is work through each of those regions in order. We'll go from long wavelength to short wavelength, and then I'll give you an example value for the wavelength and frequency at each point. So we'll start off with radio waves. They have the longest wavelength. Wavelength, example, 10 to the power of 2 meters. Frequency, 10 to the 6 hertz. So that's radio waves, those are the longest. Then we have microwaves, they're a bit smaller. 10 to the minus 2 meters, and frequency of 10 to the 10 hertz. Okay, so this is not drawn to scale, okay, just indicating that they're getting smaller wavelengths. Then we have infrared, 10 to the minus 5 meters, and 10 to the 13 hertz. Okay, you'll see that those are related according to the equation of C equals F lambda. Shorter still, then we come into the visible region, visible light, wavelength about 10 to the minus 7 meters, and a frequency of 10 to the 14 hertz. Next up is ultraviolet, 10 to the minus 9 meters and 10 to the 17 hertz. Now, one of the things I want to point out here is, like, when you're trying to think what order the waves go in, you've got visible light, okay? And that's in the middle of all the regions. Now, red is the longest wavelength, okay? So beyond the red, you have infrared. And then violet is the shortest, and beyond the violet, you have ultraviolet, okay? So that might help you get some, in the ones in the middle in the right order, and then longest wavelength, radio, shortest, we'll see is gamma. X-rays next up, 10 to the minus 10 meters and 10 to the 18 hertz. So those are X-rays, and then we have the last one, the shortest, gamma rays, shortest wavelength, 10 to the minus 12 meters, and highest frequency. There's a lot of overlap between X-rays and gamma rays, okay, with frequency and wavelength. So X-rays and gamma rays will often do similar things, but we see there is a difference between them. Right, let's look at the properties of what electromagnetic waves are. Their nature is that they are oscillating electric and magnetic fields, so that's why we call them electromagnetic waves, or electromagnetic radiation. The oscillations in those fields are perpendicular to the direction that the wave travels in, therefore they're transverse waves. And also those electric and magnetic field oscillations are perpendicular to each other. So if the magnetic field was oscillating in the horizontal plane, then the electric field would be oscillating in the vertical plane. So they're perpendicular to the travel and to each other. Now, electric and magnetic fields can also exist in vacuums, and that enables electromagnetic waves to travel through vacuums. If the fields can exist there, then the oscillations can exist in vacuums, so waves can travel through, the EM waves can travel through vacuums. That's how infrared, visible light and ultraviolet reach us from the sun. And then, of course, we detect all sorts of other electromagnetic waves from space as well. So space is a vacuum, pretty much, so they can travel through it. Then we have the speed. Electromagnetic waves travel at 3 times 10 to the 8 meters per second in a vacuum. Sometimes vacuum is called free space as well. If they're travelling through other media is of course going to have a higher density than a vacuum, so air has a higher density obviously, and therefore they will travel slower than glass, if they can travel through glass, that is, the waves in question then they will travel slower there as well. So light, for example, slows down in glass and air. Methods of production. Now, I just said earlier that X-rays and gamma rays, there's a lot of overlap with the frequency and wavelength. What's different about them is how they are produced. So let's have a look at the methods of production. Radio and microwaves are produced by oscillating electrons in aerials. Infrared, visible light and ultraviolet, they're all produced by electron energy level transitions, and we'll come to see what that means when we look at atomic energy levels. But those three are produced in that way. And then X-rays, when electrons, very energetic electrons, experience a large deceleration, you produce X-rays. And gamma rays are produced by nuclear decay. So you can see, even though there's a lot of overlap with X-rays and gamma rays, the method of production is different. Those are the methods of production. Why do we care about electromagnetic waves? Well, they're very useful. We use them a lot, so here are some examples. Radio waves, we use them for communication, like broadcasting TV, radio communications between aircraft and air traffic control sensors, and between aircraft as well. Radar also uses radio waves. Microwaves are also used in communication, and of course we use them in cooking, when we use them in microwave ovens. Then we have infrared. Infrared is used in remote controls. You can actually see that infrared in remote controls by using a smartphone camera or some other digital camera. If you take a remote and you start pushing the buttons and look at it, you won't see anything. But if you put your camera in front of it, you should see a little white flash, and that's the infrared signal that the remote is broadcasting to, in this case, that projector up there. So infrared rays used in remote controls, telecommunications, and also in cooking, because infrared transfers heat. Visible light, well, obviously you use visible light to see firstly, and then visible light is also used in telecommunications. So the telecoms here, I'm thinking of fibre optic communications. Ultraviolet is used for security marking devices. It's also useful for your skin, your biology, because your skin, when exposed to ultraviolet radiation, produces vitamin D, which is important for your bones and teeth. So, vitamin D production. X-rays are used for medical imaging and for radiotherapy. There are two types of radiotherapy. It's used in megavoltage therapy and superficial, but that's just additional detail, you don't really need to know that. And then gamma rays, they're used in medical tracers, where you implant a tracer into the body that's going to move around a particular biological system in the body that you need to investigate, and as it moves through there, it's emitting gamma rays, and we detect the gamma rays so we can locate where it is in the body. And they're also used in radiotherapy. This is the third type of radiotherapy, which is called teletherapy. And those are some uses of electromagnetic waves. Now let's look at two spectra, two regions in the electromagnetic spectrum in more detail. We'll start by looking at the visible spectrum. Each region that I've mentioned, those 7 regions, radio waves through to gamma rays, they are themselves a spectrum. So each section has a range of frequencies and therefore wavelengths. The visible spectrum has a range of wavelengths, and each wavelength or each frequency corresponds to a particular colour that your eye can receive. So here's the spectrum, and the range, you can see there's a fuzzy line at the violet end, which is the short wavelength end, and there's a fuzzy line at the red end as well. So the end is not clear cut, it's not distinct, it's not like a sharp end to visible light and a sharp end at the short end and the long end. the visible spectrum blends into the UV and blends into the infrared region. And it's possible, particularly with a lot of security cameras that are on the market now, to actually detect the infrared here. And so if you looked at the spectrum, if you produce one of white light from a filament bulb, then you would be able to see the infrared there. It show up like a big white area. That's one of the experiments we do, so you can see the infrared there. Anyway, so you can see that the end of the UV spectrum is between 350 and 400 nanometers. So it's about 370 nanometers, and it's going up to about 650, 700 nanometers. If you just stay 350 to 700 nanometers, that should be okay. So, and you can see that blue light, ultraviolet light, they're down here at the 400 to 450 nanometer mark. So whenever you receive electromagnetic radiation with that wavelength, your eye can perceive that as blue or violet light, depending on where exactly you are. And then red light has a wavelength of about 600 nanometers. So when you, that was 650. So when you receive electromagnetic radiation with a wavelength of 650 nanometers in your eye perceives it as red light. Well, your eye and your brain. Okay, so those, there's that blending in, and you need to know the order of colours, and you also need to know rough wavelength values for those. So we've got, going from long to short, red, orange, yellow, green, blue, indigo, violet. So you need to know those colours in order, and you need to know that violet has a wavelength around 400 nanometers. In the middle you're on about 550 nanometers, and then 650 for the long end. And because we're talking about 550 nanometers, that's 5.5 times 10 to the minus 7 meters. Okay? Alright, anyway, that's the visible spectrum. The next spectrum we want to look at in a little more detail is the UV spectrum. What we do with this spectrum is we divide this into three smaller regions, like three subspectra, if you like. So we've got UVA with a wavelength range of about 400 to 320 nanometers. So you can see these are all shorter than the visible spectrum. UVB 320 to 280, and UVC 280 to 100 nanometers. Or, you know, there is some blending in with the visible spectrum because it's not distinct beginning and end. Now the sun produces all three types of UV radiation. That's because it's so hot. It's incredibly hot. So a light bulb produces no UV, sorry, it produces no UV. It produces visible and infrared because of its heat, its temperature, but the sun is much hotter, so it also produces UV, and it produces all three types of UV. UVA is closest to the visible spectrum, then this is next along UVB, and then UVC is the highest frequency UV radiation. So you just need to know some rough wavelengths for each type of UV. UVC is very harmful, but almost all of it is absorbed by the ozone. It's harmful because it's so energetic. Then UVB, it has a good feature. That's the UV radiation that produces vitamin D on the skin. It's bad also because it damages DNA in skin cells, which can lead to skin cancer. So UVB does that. Some of that does get through to ground level. That's necessary though because we need that vitamin D. Okay, sunlight is usually the main way you get vitamin D. And then UVA, whether you consider this good or bad, it tans your skin, but it also wrinkles your skin. So maybe you think that's good because you like to have a tan, but a lot of cultures don't think tan skin is cool, so that's bad. You might think it's bad that your skin wrinkles, but then maybe you like to look old and wise. So it's good or bad, up to you. Anyway, then this is bad, causes cataracts to form in your eye. So UVA. Sunscreen filters out UVB, and sunglasses filter out UVA and UVB. And you'll often, if you buy a pair of sunglasses, it'll often say that it filters out UVA and UVB. That's what they're talking about. And yeah, the sunscreen may well say it filters out UVB. So it's got chemicals in there that absorb it, prevent it getting to your skin. Okay? If you get security markers, in fact, which glow when exposed to ultraviolet radiation, you can try this. If you've got a UV lamp and a security marker, you can write on something, shine UV on it, and you'll see it. Put some sunscreen over it, shine on it, and you won't see it, because the chemicals prevent the UV reaching the ink. Okay, so that's our look at the electromagnetic spectrum. We've looked at two in a little more detail. Any questions? Cool. A but. We have a but. Now, I've been talking about electromagnetic radiation as waves, because if you remember, in the history of our understanding of electromagnetic radiation, Newton thought that it was a stream of particles, and Newton, big dude in physics, so you go along with what he says, because he was bang on with a lot of stuff, though of course subsequent theories have superseded him in a few places. Anyway, then Young came along and proved that electromagnetic radiation was waves. Now we have the photoelectric effect, and that was a problem for waves. Seems to suggest that actually electromagnetic radiation is a stream of particles, so we seem to be going back to what Newton thought, but for different reasons. Anyway, so we've treated electromagnetic radiation as waves so far, but what if it is actually particles or something else? Let's have a look at this experiment then. The photoelectric effect, which I've just mentioned, is problematic for wave theory. Here's our experimental setup. This is using a gold leaf electroscope. There's our gold leaf here. What an electroscope does is it measures charge. Whatever is attached to the stem, if it's got a charge, then the electroscope indicates that by the gold leaf being repelled from the stem. Because the gold leaf and the stem have the same charge, then they would repel from each other. So if the stem is negative, then the gold leaf, because it's attached, is also negative, and it moves away because they repel each other. If it's neutral, then the gold leaf's not going to sit there suspended in air, it's going to fall because of its weight, that moment produced by the weight. Okay, so it's going to fall down. Likewise, if it's positively charged, it will also move away. Okay? Now what we do in the photoelectric effect is we attach a metal plate to the stem. We're going to use a zinc plate in this case. And we make sure the surface is nice and clean. And we negatively charge that plate. Now the photoelectric effect does not work if the plate is positively charged. It needs to have a negative charge. Then we take a light source, let's start with visible light, and we expose the plate that is negatively charged, so the gold leaf is repelled from the stem, and we expose it to visible light. And we keep that light shining on that plate for a nice long time, and nothing happens. So you expose the plate to visible light and nothing happens. So we've got a negatively charged plate. That's what the electroscope does. Expose the plate to visible light and there's no change. Now let's expose it to ultraviolet. So we switch our light source for an ultraviolet lamp, and the leaf falls immediately. Okay? Doesn't take effect afterwards, begins to fall immediately until it's fallen all the way down. So what we see is that because it is negatively charged, there were extra electrons on the metal plate. And the ultraviolet was able to remove the electrons from the surface of the metal plate, and therefore return the metal back to a neutral state, because all the negative charge was removed. So the gold leaf falls. Now, the gold leaf does not then go up. So the UV is not transferring positive charge to it. it's just removing the negative charge, okay? So we know that it's removing electrons, that's what it's doing, okay? If it was transferring positive charge, we'd see the leaf fall and then it go back up. And also, if you started off with a neutral setup and expose it to UV, then the leaf would begin to move away, but that doesn't happen, okay? It only works if you start off with a negative plate and the leaf only falls down and that's it. And as I said, it happens immediately, okay? So, UV can remove electrons from the plate. Visible light cannot do it. It doesn't matter if you left that for hours with visible light. A nice bright visible light on it, it's not going to change anything, okay? So, this proves a problem for wave theory. What's the problem? Waves transfer energy continuously. Wave energy is related to intensity. So, visible light should release electrons if A, you expose it for long enough, or B, expose it to light of high enough intensity. If you left it for long enough, then eventually the light would transfer enough energy to give the electrons energy to escape. Okay? But that doesn't happen. And if you had a high enough intensity, nice bright visible light, high intensity means lots of energy being transferred, so those electrons should gain energy to escape from the metal plate, but they don't. Visible light cannot remove electrons from a zinc plate at all. Also, frequency should not be a factor of electron removal, but it is. When we went from a visible lamp to an ultraviolet lamp, we increased the frequency. That shouldn't affect this, according to wave theory. But it does. So this is a problem for wave theory. Okay? Does that make sense? Cool. So, photoelectric effect. A new theory. And we start at the turn of the 20th century. This man here, Planck, who lived in Germany, 1858 to 1947. Max Planck, he postulated a new theory about electromagnetic radiation. The reason he did this was because in his experiments that he was doing, that he was having trouble with the calculations. So this led him to put forward a new theory about electromagnetic radiation. Now I should note here, he did this reluctantly. He did not want to do this at all. Okay? It's a very reluctant move, but it worked. So what he did was he assumed that electromagnetic radiation transferred energy discretely, like particles transfer energy. And hey, that solved his problems. Amazing. So he did this thing under duress. He didn't want to do it, but it solved all of the problems he was facing in his calculations. Then comes Einstein, okay? And he lived 1879 to 1955, also in Germany. And he built upon this new idea that electromagnetic radiation was transferring energy discretely. And he used it to propose a new solution for the photoelectric effect. And it was for this that he won a Nobel Prize, his work on the photoelectric effect. So he said that electromagnetic radiation consists of particles called photons. Anyway, I'll say a little bit more about that in a moment. So now what we see is that electromagnetic radiation, under some conditions, it does behave like a wave. Double slit experiment, for example, polarization. And under other conditions, it behaves like a particle. So it seems that electromagnetic radiation has a dual nature. Normally, we don't observe that dual nature simultaneously. You don't see electromagnetic radiation behave like waves and particles at the same time. However, there is a recent experiment that seems to have done just that, but I'm not going to talk about that now. Let's move on to look at these things called photons. Electromagnetic radiation consists of photons, and what photons are they are quanta of energy. A quanta means like a small amount of energy. It's a very small amount of energy, in fact, but the point is it's a discrete amount of energy. You can think of it as like packets of energy as well. And their energy is dependent upon their frequency. Their energy is equal to hf. H is the Planck constant, and that is 6.63 times 10 to the minus 34 joule seconds. So Einstein proposed these photons, the idea of these photons, and you can see that he's building on Planck's work by using this constant, the Planck constant. So how does this new approach explain the photoelectric effect? Metals have a work function. Phi is the work function, and that's equal to Planck's constant multiplied by F0, where F0 is the threshold frequency. This work function is the minimum amount of energy required to emit electrons from the metal plate, the negatively charged one. And that's related to F0. It's like a threshold frequency. It is the threshold frequency, I mean, but what it's like is that's the minimum frequency at which you emit electrons. Okay, so you've got that's the minimum energy and that's the minimum frequency. You can see that this follows from E equals hf. Now, these photons, they are transferring the energy in these little packets, these quanta of energy. And one photon can give its energy to one electron. That's important that you appreciate it's a one-to-one interaction. If the photon does not supply enough energy, then no electrons are emitted. If the electrons on the metal plate do not get enough energy from the one photon that interacts with them, then they can't escape. So the photons need an energy that is greater than or equal to the work function. They need to reach this minimum amount of energy. In the case of our zinc plate, the visible photon energy is less than the work function. So visible photons cannot remove electrons from the zinc plate because the photons don't have enough energy. But UV photons, they do have enough energy. They have energy greater than the work function, so the electrons can be emitted from the metal surface. Okay, so because these UV photons, UV, higher frequency, means they've got more energy, they have enough energy to take them over that threshold value. The energy that's left over is converted into kinetic energy in the electrons. So the electrons gain kinetic energy once they've escaped the metal. So they're ejected from the metal, they have kinetic energy afterwards. Which leads me to talk about the photoelectric equation. So the kinetic energy, I should say this is the max kinetic energy. The maximum kinetic energy that an electron can gain is the energy of the photon minus the work function. So the difference between there goes into the kinetic energy. Now, not all electrons require exactly the same amount of energy to escape the metal surface. Those nearer, right at the edge of the surface, they will require less energy than the electrons below the surface. So this represents the kinetic energy that an electron right near the surface will gain. Okay? And you can rewrite that as well. The maximum kinetic energy is hf, that's the photon energy, minus hf0, which is the work function. And you can take the f out and write that as f minus f0 there. Right? You can plot that on a graph as well. So here's our max kinetic energy. Watch out for scales here, especially because you're dealing with very small amounts of energy, very high frequencies. So often this will be 10 to the minus 19 joules and 10 to the 14 hertz. If you plot the graph for max kinetic energy against incoming photon frequency, then you get a graph like this that has an x-axis intercept here, and that's the threshold frequency. So if the frequency is less than this value here, you're not releasing any electrons, and the gradient is the Planck constant. Also, if you continue that line down here, where you get a y-intercept, that'll be the negative of the work function. So that's the graph. And as I said, watch out for those powers of 10 in the scales. Okay. Now, I said that intensity does not affect whether electrons are emitted or not. Okay? And that is true. But intensity does have an effect on the experiment, on the photoelectric effect. Intensity tells you the amount of energy arriving per unit time per unit area. Okay, so it's like the total amount of energy arriving at our metal plate per second. So, if we have higher intensity, that means we've got more energy, and that would mean, how is that energy made up? It's made up as photons, so we get more photons arriving. So the intensity affects the number of photons arriving per unit time. Let's apply that to our zinc plate and the photoelectric effect. If we have high intensity visible light, then we've got lots of low energy photons arriving. Okay? We've got loads of them arriving because visible photons have low energy. So to make up that total amount of energy, you need loads of them. Okay? No electrons will be emitted though, because the photons, the individual photons, do not have enough energy to release electrons. Doesn't matter how many you have arriving, those electrons are never going to gain enough energy to escape. So that means your gold leaf is going to stay put. It's not going to do anything. Okay? Now let's have some low intensity ultraviolet light. We've got a small amount of high energy photons. Now when I say small amount, it's still like billions of photons, but compared to this, it's a small amount. So the total amount of energy is small because it's low intensity. But these UV photons, they're higher energy, so we're going to require fewer of them to make up that total amount of energy. That's going to mean, because the UV photons can release electrons, a small amount of electrons will be emitted. So the leaf will fall, but it will fall slowly. And then lastly, we'll take some high intensity ultraviolet light. Now we have lots of high energy photons, not as many as here because those have smaller energy photons, but we have lots of high energy photons, and that's going to, because each photon can release an electron, we'll have lots of electrons emitted. And that will mean the leaf will fall, and it will fall faster than before. Okay? Now, does that make sense, or should I give you some numbers? Yeah? Good. Alright. So that's the photoelectric effect. Let's look at a related experiment, which is the Photocell Circuit. We've got two plates here connected across a power supply. So this power supply is going to negatively charge this plate and positively charge this plate. We've got to have those plates in a vacuum chamber, and if we expose this plate to our high energy photons, the UV light, then that will emit electrons from this negatively charged plate. It's negatively charged, so it can emit electrons. And because those electrons are negatively charged, they're going to be repelled from that plate now. Now they're off it. So they're going to be accelerated away from the plate, and this is positive, so they're going to be attracted towards that, and they will be accelerated across from the negative plate to the positive plate, and that will enable a current to flow because we've got a flow of charge. Those electrons are carrying charge, so we've got a flow of charge. Current will flow. If you increase the intensity of your UV radiation, then you've got a higher rate of electrons being emitted, and that means you'll get a larger current flow. Okay? Because for the reason I said before, if you've got higher intensity, that means more photons arriving that can release electrons, so you've got more electrons flowing. And it needs to take place in a vacuum because you don't want huge air molecules obstructing the flow of your electrons. If they're there, then they'll obstruct the flow of electrons between the plates. And that's the Photocell circuit. we're dealing with small amounts of energy here. So the joule, you don't want to have to keep, if you're going to use a joule, you don't want to keep talking about 10 to the minus 19 this, 10 to the minus 19 that. If you're dealing with small amounts of energy a lot, then it's helpful to have a more practical unit of energy, which in our case is going to be the electron volt. So, let's remind ourselves that the energy transferred to a charged particle which is accelerated across a potential difference is equal to this. The energy transferred is the charge on the particle multiplied by the potential difference you accelerate it across. Let's accelerate an electron through a potential difference of 1 volt, and what kinetic energy would it gain? And this will be the amount of work done in this instance of accelerating that electron through a potential difference of 1 volt we will define as the electron volt. So 1 electron volt will be equal to the charge, 1.6 times 10 to the minus 19, that's that, times 1. That's nice, 1.6 times 10 to the minus 19 joules. So 1 electron volt is 1.6 times 10 to the minus 19 joules. That means that if I wanted to convert 2.3 electron volts into joules, I just multiply by 1.6 times 10 to the minus 19. That will give me it in joules. And if I want to convert 6.4 times 10 to the minus 19 joules into electron volts, then I just need to divide that 6.4 times 10 to the minus 19 by 1.6 times 10 to the minus 19. Whew, this is a lot. Anyway, the 10 to the minus 19 is going to cancel out, so it's 6.4 over 1.6, so it gives me 4 electron volts. So that's how you convert EV to joules and then joules into EV. So that's not the answer, you have to actually work that out. It's 2.3 times that. Okay? Alright. Let's have a look at an experiment that you can use to estimate Planck's constant. We're going to use LEDs to do this. LEDs energise electrons, and those electrons are then enabled to, so they move up to a high energy state, which I'll explain in a little more detail in a moment, but they move up to a high energy state and then they drop back down, and as they do so they emit photons of a specific frequency. And we're going to use this to get an estimate for Planck's constant. So there's our experimental setup here. We've got a voltage supply, and we've got a variable resistor here, which will enable me to vary the potential difference across my LED here. Now the energy that's supplied to the electrons as they move through the LED here, we're using the same equation that we just looked at, W equals QV. And the photon that is emitted is going to have an energy of HF. So that if we assume that all of the energy given to the electron moving through the LED is emitted as a photon, then QV is equal to HF. Now, if we reduce the voltage across the LED to the point that it emits just 1 photon, then 1 electron has given its energy to that one to make that 1 photon, okay? Because it's a 1-to-1 interaction. And that will enable us to find the voltage required to produce that photon, and then of course we know what the energy is, because we know the charge of an electron. So we find that this potential difference, so we've got the photon energy. We know what frequency of photon is produced in our LED, so the only unknown is H. So that gives us a way to work out what Planck's constant is. But to make it more accurate, what we would want to do is repeat this for a range of different frequencies. So we've put a new LED in here, one that produces a different frequency photon, and repeat the experiment. We have a different voltage. Again, H is the only unknown. But what we'll do is we'll collect all of our V data and our F data and plot a graph from that. So let's have a look at the graph. So the energy, we'll plot energy against frequency, plot all of our points, and draw a line of best fit for our points, and the gradient of that line would be equal to Planck's constant. So that gives us a way to work out, to estimate Planck's constant using LEDs. Okay? So you've got to do it for a range of LEDs. Obviously, this is only an estimate because there's plenty of limitations in that experiment. There's the LED efficiency. There's the sensitivity of your eye to just detecting one photon. And if you have background light as well, that's another problem that you could face. Okay, by the way, all the experiments that I refer to, I think so far I have done videos for all of them, so you can find those also on the YouTube channel. Right, so spectra. We're going to look at elemental spectra. The spectra from excited elements. Diffraction gratings. We looked at that in the waves lesson, and what they do is they enable us to separate out incoming light into all of the frequencies that constitute that incoming light. If you take light from elements that are in an excited state, and I'll explain what that means a little bit, that light contains only discrete colours, so there's only certain wavelengths present, or certain frequencies present in that spectrum. And each element has a unique spectrum. So this is a hydrogen spectrum. You can see that hydrogen light, which normally looks purple, has some red, some yellow, and some blue wavelengths, and some violet wavelengths. Also, so the light looks purple. Once you split it up, you can see that it's constituted of these colours. So you can see that if you took white light and separated that out, you have this continuous range of frequencies present, all the way from darkest red to the darkest violet. You've got everything in there. But these spectra, they're called line spectra because they only have certain wavelengths. And as I said, each element's spectrum is unique, so if you take the helium spectrum, it will be different, sodium spectrum is different, and so on. So these different spectra are all unique. And whenever you produce light from hydrogen, you always get this spectrum. And when you produce the sodium one, you always get the same spectrum. So it's always the same, it's not random, it's always these specific wavelengths that are emitted. Okay? Now this was well known for centuries that you could do this, but the reason for it was not well known, or was not known. So one of the ways that this is done is you take a sample of some metal, you burn it, and so you're energizing the atoms essentially, and then you look at it through a spectroscope which has got diffraction grating in it, and you can see all these different colours, but only specific ones. So chemists have been doing that for a long time. You can also actually look at light coming from space, and you can see you can get similar observations, sometimes the reverse of this, which I will come to. But yeah, you can see that. So astronomers have been doing it as well, you can see this. This is discrete behaviour, okay? Very specific, well-defined wavelengths appearing. This is further evidence of the particulate nature of electromagnetic radiation. Okay, so this is further evidence. And that's how it's explained. It's light is behaving like particles again. So let's have a look at how this works then. What I just showed you there was the emission spectra, the emission spectrum for hydrogen. The explanation is that atoms have got discrete energy levels within them that orbital electrons can exist in. Okay, they can only exist at those well-defined, specific, discrete energy levels. So we're explaining this discrete behaviour. And electrons can transition between those energy levels, but energy must be conserved in order to do so. An emission spectrum is produced when electrons transition to a lower energy level. If they go from a high to a low energy level. So I'll show that here. E1 is a higher energy level than E2. If the electron drops an energy level, then the electron has lost energy. Where did that energy go? It was emitted as a photon. So that photon was produced, and the photon energy corresponds exactly to the difference in energies of those two levels. So that's how it was produced, and that's why it's called an emission spectrum, because it emitted a photon. This is a spectrum for sodium. Now you probably can't tell, there are actually two lines there, but they're so close together that normally when you look with the naked eye anyway, you only see a single line. There are actually two lines that are very close together. So this is an emission spectrum for sodium, and it contains, in the visible spectrum, just two wavelengths. Okay, so there's just those two. Most of it is dark because those wavelengths are not produced. So you can imagine if you had a continuous spectrum from a white source, you'd have the white region there, red, going all the way over to violet. But with this sodium lamp, we're only producing two wavelengths. So we've got a couple of energy level transitions taking place with the orbital electrons in sodium, just two producing two photons. So only some of the wavelengths are emitted. Most of that spectrum is empty. The flip side of an emission spectrum is an absorption spectrum. Electrons can transition between those energy levels just as before, but we've got to conserve energy. So to move up an energy level, then electrons require energy from somewhere. Where do they get that from? Photons can supply that energy. So if a photon is absorbed, then the electron gains energy. And if that energy corresponds exactly to the difference in energy levels, then it will move up to the new energy level. Absorption spectra, they contain all of the wavelengths in a range, but some are missing. So here we've got the electron moving from E2 to E1. It's moving to a higher energy level because it absorbed a photon to do so. So here's our continuous spectrum, and there's our two wavelengths missing. So white light has passed through a cloud of vaporized sodium, and as it did so, the electrons in the sodium absorbed those two photons so that electrons could move up an energy level. So one electron moved from one energy level to another in absorbing that photon, and another electron moved from one energy level to a different energy level to correspond to exactly that amount of energy. The energy levels wouldn't be particularly different because those wavelengths are so close. So as I said, if you have white light incoming on a cloud of a particular element, and as the white light moves through that cloud of element, or that cloud of gas, like maybe hydrogen or helium, as they move through, some of those photons are absorbed by the electrons in the atoms, enabling them to move up energy levels. But the photon energy has to correspond exactly to a difference in energies. And that's why astronomers could observe these absorption spectra. So you had, when you burn substances, you can see the emission spectrum, but here this is light, particularly coming from space. It's moved through a cloud of some element, and you can see wavelengths missing. Energy levels are these energy levels within the atom are represented with schematic diagrams. So here's an example schematic. Energies here measured in electronvolts, that's more practical. So we've got 0, -2, -4, -13, -22. N equals 1, so that's the first energy level, then 2, 3, 4, 5, and so on. And this top one is N infinity. The lowest level is called the ground state, and all of the other energy levels above that, they're the excited states, okay? So this is like to say, if something has got more energy than it normally would have, it's excited, because why not? Okay, And the highest energy level, which I've called n equals infinity, that represents if an electron gains enough energy to move to that energy level, it's gained enough energy to escape the atom. Okay? And the energy levels have negative values because a free electron, which is one that is here at infinity, is defined as having 0 energy. But obviously these are lower energies, so how do you get lower energies if that's 0? Well, they're by making them negative. Okay. Photon energy must correspond exactly to the difference between energy levels if it's to be absorbed, and if a photon is emitted by electrons dropping energy levels, then its energy will correspond to the difference between those energy levels. So E1 minus E2, that's the difference in energy level, and HF is photon energy. Let's have a look at a photon being absorbed. So we've got a photon, an electron in the ground state absorbs a photon. The photon causes the electron to move from this ground state to n equals 3, the third energy level. So E1 is minus 4, E2 is minus 22. So the photon has to have energy equal to minus 4 minus 22, giving us 18 electron volts. So that photon had 18 electron volts worth of energy. If it had 17 electron volts worth of energy, it could not be absorbed because the electron could not move up to any of these energy levels. It can't move up part way. It has to move up exactly to an energy level. So 18 will enable it to move exactly to that energy level so it can be absorbed. Also, it couldn't be 19 because it can't go just above it either. Okay? So the photon had an energy of 18 electron volts. That's just an example of using that equation. And then a photon is emitted by an electron that was in an excited state. It was at the fourth energy level here. And as it dropped down here from minus 2 to minus 22, minus 2 minus minus 22 gives you 20 electron volts. So the photon would have an energy of 20 electron volts in order to make that transition. Okay? So that's how those energy levels are drawn. And this is all about the conservation of energy. Okay? Then matter. What about matter? Louis de Broglie, he said, well, if electromagnetic radiation has a dual nature, then maybe matter particles do too. That was his idea. And so here we're thinking of things like electrons, neutrons, protons, things that we've always thought of as particles. Maybe they have a wave nature, or they can behave like waves as well. So the hypothesis that he stated was that moving particles can behave like waves. It's important that they're moving because their wavelength is going to be related to their momentum. Okay? And also, they can only behave like waves if the conditions are right. Just like electromagnetic radiation, it can only behave like particles if the conditions are right. And it can only behave like waves if the conditions are right. So if we have the right conditions. Particle wavelength is related to the particle's momentum according to this equation. That's what Louis de Broglie hypothesized. The wavelength is equal to h divided by the momentum. So if a particle is stationary, then it can't have a wavelength associated with that. Okay? This hypothesis was confirmed. Particle diffraction and interference was subsequently observed experimentally. A beam of electrons was fired through a thin sheet of graphite, and as it did so, it produced a pattern of light and dark rings like this, and that is a two-dimensional interference pattern. The screen that they're being fired onto is fluorescent, so wherever electrons strike it, it causes it to glow. So we're getting this pattern of light and dark rings, just like Young's double slit experiment, light and dark fringes. And the reason that this arose is because there's a regular spacing in the crystalline structure of graphite, and that behaved like a diffraction grating. but obviously it's two-dimensional, so it's that's why you get two-dimensional interference pattern. Now let's compare this type of pattern with something that we know behaves like waves produces too. So let's take X-rays and electrons. And what we get is this. This is an interference pattern produced by X-rays passing through an aluminium foil. Here's the pattern from electrons passing through the same foil, and you can see that those patterns are pretty much identical. Okay, there's some slight subtle differences, but basically they're doing the same thing. So we are getting an interference pattern that corresponds with something that we know is wave behaviour. And also the equation was confirmed as well. Remember the equation, wavelength is Planck's constant divided by the momentum. The wavelength that this predicts for a particular experiment was 1.67 times 10 to the minus 10 metres. The wavelength that was measured experimentally was 1.65 times 10 to the minus 10 metres. You can see an uncanny similarity. This is bang on. So yes, this is confirmed. The data is confirming the hypothesis. And also, the experimental wavelength and speed are inversely proportional, which is also corresponds with the hypothesis. So it's all consistent, it all works. So matter has a dual nature, just like electromagnetic radiation does. So, when I have a class and all my class of students come through the door, why don't I get an interference pattern being formed on the rear wall there? Why don't classes of students coming through the doorway produce an interference pattern? Well, let's work out the wavelength for a student walking through the door. Okay? Planck's constant, 6.63 times 10 to the minus 34, that's the h, divided by the mass of a student, let's say 70 kgs, and let's say they go through the door at 1 metre per second. Calculate that, and their wavelength is 9.5 times 10 to the minus 36 metres. So what you can see is that is incredibly tiny compared to the gap provided by the door. So gap, much larger than the wavelength, no diffraction, no interference pattern. Thank goodness that my students don't produce an interference pattern on my rear wall. And that is quantum physics. Hope that was helpful. If you've got any questions, you can put it in the comment section down the bottom, or Twitter, or whatever. All right.